Now, how to apply this idea of random walk in practice? First of all, you need to account for the presence of sinks, so nodes having no outgoing edge. This would correspond for the example of the web graph to a page having no link. So in this case, the idea is very simple. You just force the random walk to restart. So basically, you will select the next node uniformly at random among all nodes, including the node itself. Okay, so in terms of adjacency matrix, this means that whenever you have a row of zeros, you will replace this row by a row of ones. Of course, you won't do that, otherwise you would get a dense matrix. You will, in practice, store A plus the vector of things times this vector of ones. Okay, S here is a set of nodes having no outgoing edge. Okay, you will store this structure to make your matrix vector multiplications. Now, there's another issue with random walks, which is the presence of traps. Imagine you have another node here, which is connected to what was a sink before. So in this case, you don't have a sink, but if you walk in this graph, at some point you will be trapped in the set of two nodes. Okay, and so you will conclude that these are the most important nodes in the graph, which is probably not the case. So again, to escape from these traps, you can force the random walk to restart. And basically what we'll do is that we'll generate this ID and force the restart from any node with some probability. Okay, so from any node, either you follow the edges, so here these edges, with some probability alpha, or you restart from a node selected uniformly at random with probability 1 minus alpha. Okay, and this is basically the idea of Pagerank. So you have a parameter alpha between 0 and 1 that will control the restart probability. So from any node, you walk with probability alpha at random, or you restart to a random node, for instance, uniform distribution, with probability 1 minus alpha. And this defines now irreducible Markov chain. So reducible, which means that now the graph is strongly connected. And also, you don't have problem of periodicity. The Markov chain is aperiodic. And the transition matrix is just that one. Okay, P, it depends on the parameter alpha. And so you need to solve, if you like, to find the stationary distribution, which we call the Pagerank vector. You need to solve the balance equation as before. So we'll denote this vector by P alpha. So you need to solve this equation, and you know that there is a unique solution. Okay, and this is a Pagerank vector. So for the computation, you can either try to solve it exactly, or again use these power iterations, and it is the same idea. The point is here that here you have a sparse matrix, and here you have just a vector. So this is an example for this graph. So it's a very general graph in the sense that you have a sink, you have a source here, but thanks to this restart mechanism, you will visit all nodes infinitely often, and you can really define this frequency of visit of each node, which is a number between 0 and 1. But of course, the solution actually depends on this parameter, which is known as a damping factor. And it's interesting to have a look at this default value, which is O.85, okay, which was proposed originally by Google's founders. Actually, you can have a look at the path of the actual random walk before restart. Okay, so how many nodes do you visit before a restart? Let's say we have nothing, and it has a geometric distribution with parameter 1 minus alpha. Okay, because starting from a node, you will move to another node following the random walk with probability 1 with probability alpha, and we start with probability 1 minus alpha. And the same for the next one. You will move to another node with probability alpha, and so on. And so the number of nodes you visit before restart has a geometric distribution with parameter 1 minus alpha. So in particular, if you look at the expectation is alpha over 1 minus alpha. And this is, so it's almost 0 is alpha tends to 0, it tends to infinity if alpha tends to 1. And for the default value of O.85, you find something like 5.7, which makes sense actually, because it means that if you think of the 6th degree of separation of typical social networks, for instance, in practice, after 5 or 6 hops, you have visited almost all the graph. Well, you can have visited. I mean, almost all nodes are accessible in 5 or 7 hops. So finally, there is a explicit expression of the Pagerank vector with respect to pi of t, which is again the distribution of the Markov chain for a pure random walk, starting from a uniform distribution. Okay, so the initial distribution is uniform over 1n, and you assume you walk t for t time step, and you look at the distribution, call it pi of t. It turned out that the Pagerank vector is just the smoothing average of these vectors at times t equals 0, 1 till infinity. Okay, and you can quite easily prove this result by just, you need to prove that pi alpha solves the dependence equations. So your job is just to replace p of alpha by its expression and verify the equality. Now, this expression is interesting because you may have a look at what happens in the limiting case, for instance, where alpha tends to 1. When alpha tends to 1, actually pi alpha will tend to pi, which is the stationary distribution, so the limit of pi of t, so the stationary distribution. So for instance, if you think of a undirected graph, this would correspond to the distribution which is proportional to the degrees of the nodes. Now there's another limiting case which is interesting. When alpha tends to 0, what happens is that pi of alpha would be pi of 0 plus alpha times pi 1 minus pi 0 plus small O of alpha. Okay, so in terms of ranking, you will rank your nodes, since pi of 0 is uniform, in terms of pi of 1, And pi of 1, if you come back to the first lecture, pi of 1 is just what we refer to as a neighbor sampling. Okay, so if you let alpha tends to 0, what you obtain as a ranking is the same as the one you would get with a neighbor sampling.